Okay, we'll go ahead and we'll go ahead and get started. Uh, Couple of administrative notes. Remember, you have a homework due next week, and also I'll let you know for sure next week. But I'm thinking of having the final exam for this class on the last day of class, which would be Tuesday, December 5th. So check, it'd be from 5 to 7 during, 5:15 to 7:15 during the class time. So check your calendars to let me know if there's any issues. And I'll also post it as an announcement so those folks who aren't here can also check. Just adding figuring out how to schedule things is like currently I have the exams for both of my classes scheduled at the same time. That won't work. So just in bouncing off and what I already know from people's schedules. So I'll talk about this on Thursday, but obviously for those of you who are also in the my finite elements class, that'll mean that your final will be on the scheduled time of December 14th. So anyways, but for this class, tentatively final exam on December 5th. Let me know. And obviously we're a month away, but it'll probably be like half from the midterm, half since the midterm. But again, much more details when we get closer. Also, course registration for next semester is open because several of you have asked. I'll be doing 2 classes next semester. I'll be doing a advanced composite micromechanics of composites class, which will be on Monday nights from 5:15, at 5:15 the one night a week, and then we'll be doing finite elements 2 on Thursday nights. So if you're interested in either or both of those classes, I encourage you to sign up. So any other questions on administrative items? Okay. If not, come in. We will go ahead and get started. So we are going to plow through and finish our elastic discussion of elastic plastic fracture mechanics tonight. And then starting next week, what we'll do for probably at least a couple weeks, granted there's not that long left in the class, but for a couple weeks is we'll start talking about detailed fracture mechanics testing. So how some of these various parameters that we've talked about the theoretical aspects of, such as the stress intensity factor and crack tip opening displacement, J integral, etc., practical ways of measuring those in the laboratory. But for tonight, we'll introduce the topic, but tonight we'll finish up it'll be I have the notes to finish it up. It'll either all the way through tonight or just depending on timing, we'll see how it goes. If we have to finish a tiny bit next week, we'll be finishing up our discussion of elastic plastic fracture mechanics. So just be cut to this will be repeating the last little bit of what we did last week, just because realize when I looked through, I kind of cut off more than in the middle than I'd wanted to, but talking about, at least from a theoretical basis, issues with determining the J integral, one of the ways of quantifying the equivalent of the strain energy release rate for elastic plastic materials, that Rice showed that it was possible to determine J directly from the load displacement curve of a single specimen. And they looked at a couple of specimens in particular. So we talked about right through at the end of class last week. One of the specimens they looked at was a double-edged notch tension specimen of unit thickness, and assumed that there were cracks on either side of the specimen, and the crack tips are separated by a little bit of material of length 2b. And for this material that the area of the crack can be found to be twice the increment in area. As the crack grows, the increment in the crack area is twice the increment, the increase in A, the length of the crack, which can also be found to be equal -2 times the length of the distance, the equal to the increment in the distance between the cracks. And obviously the cracks go longer, the distance between the cracks will grow shorter. So we talked about last week, we can take the definition of the J integral that we talked about and modify it accordingly. And we can say that J is equal to 1/2 of the integral from 0 to the load we apply, because remember in all this, we're assuming that we're applying an increasing load, and we're seeing how the crack changes with the increase in load. So integral from 0 to the current value of applied load to the derivative of the resulting displacement with respect to crack length, for the fact, specifying that we applied the load, and we integral dP, and we can be found that it's equal to -1/2 the integral from 0 to P again of the change in our displacement. And this displacement's all the idea that when you do a fracture experiment, you're usually measuring load displacement curves. So the derivative of the displacement with respect to the distance, half the distance between the cracks, again, all this idea for constant load. And we can do the switch again because of this relationship here. So in order to compute J from this expression, we need to determine the relationship between the load and the displacement and the dimensions of our panel. So we're assuming an isotropic material that obeys the Ramberg-Osgood stress strain law, that nonlinear elastic law we talked about last week. From a dimensional analysis, you can determine that the displacement is equal to the distance, half the distance between your cracks, times some function of the load over sigma naught, which was one of the constants in our Ramberg-Osgood related to the yield stress, times B, and also a function of the crack length divided by B, and the sigma naught parameter in the Ramberg-Osgood law divided by the modulus, and Poisson ratio allowing for the possibility of plane stress, and the other constants in the Ramberg-Osgood law, alpha and n. So again, this is just some non-dimensional function now that our displacement is related to a function of all this. Now we'll be able to simplify things a little bit, that for fixed material properties, we're assuming the material properties don't change with time. We only need to consider the load and the specimen dimensions. And you can take your displacement and you can break it up into an elastic component of the displacement and a plastic component of the displacement. So if we take this idea and we substitute it into this expression here, what we'll effectively do is we'll take this and we'll break it up into an elastic component and a plastic component. So specifically, we can say that J is equal to -1/2 integral from 0 to P of the derivative of the elastic part of our displacement with respect to B for a constant, for under load control, plus the derivative of the plastic part of the displacement with respect to B for the case of constant load, all integral over the load. And this elastic part is easy. We can find that's just equal to the square of the stress intensity factor divided by E prime, where remember for plane stress, E prime is just equal to E. For plane strain, there's also Poisson ratio terms running in around in there. Minus 1/2 the integral from 0 to P of the variation in the plastic part of the displacement with respect to B integrated over dP. And so therefore, we only need to worry about the plastic displacements because the solution for the elastic component of J is already available. It's just the standard stuff from when we did all of our discussions of linear elastic fracture mechanics. Now we can also assume that because all our stresses are concentrated right in this region here between the cracks because of the crack tips. So a reasonable assumption to make is that the plastic deformation is confined to the ligament between the crack tips. And because of that, we can assume that the length is the only that this B, the distance between the cracks, is the only length dimension that influences the plastic part of the displacement, because that's the only place where any notable displacement is going on. Now, obviously, as I kind of hinted at before, the key to this assumption is you have to assume that your panel has a deep enough notch so that your increase in stress in the area between the ligament is substantially higher than the remote stress in the overall cross section. So we just make sure the notches are deep enough, the stress intensity factor is high enough, which makes the stresses high enough that the only place where any action is going on is that area between the cracks. So with all that, we're going to define a new function for the plastic displacement. We're going to say that it's just equal to the distance between the cracks and some function of the load some function divided by the load divided by this half distance between the cracks. And we're going to assume, because since we assume that the plasticity is only taking place between the cracks, we don't have to worry about what's going on in the region of the crack length. So taking a partial derivative with respect to the ligament length D, we can say that so we take this expression and we differentiate it. So the derivative of the plastic part of the displacement with respect to B is equal to, by a chain rule type of thing, this function h of P over B, because we differentiate out the B, and then minus H prime, because B's in the denominator, of P over B times P over B. So now we have to determine what's this derivative H prime. So to do that, we take the derivative of this with respect to load. So when we do that, we get that the derivative of our plastic displacement with respect to load for, looking at B for a constant B is just H prime of P over B. And it's just, and we have is the chain rule derivative inside of here, we get derivative of this with respect to p is 1 over b, which cancels out with the b that was in the, effectively numerator here. So that's where things cancel out. And from that, so when we take all this and we substitute it in what we have here, and we take this definition of H of P over B is equal to our plastic displacement divided by B. So when we take this and we take this and we substitute it in here, what we end up with is that the derivative of the plastic part of our displacement with respect to B for the case of applied load is equal to 1 over B of the plastic displacement minus P times the derivative of plastic displacement with respect to the load for the case of constant B. And yeah, that's it. Okay. So then we take this and we substitute it into, where am I looking for? Here. So we take all this we found. So we found this now, so we can substitute it in. And what we get in after all, and we do some math games integrating by parts, H too far in my notes. What we get up with is that J is equal to the square of the stress intensity factor divided by E prime plus 1 over 2 times B times 2 times the integral from 0 to the plastic displacement of P times d delta P minus P times delta P. And, just at least from a theoretical point of view, this is something that we can measure in the laboratory, because if we have our total displacement and we subtract off the elastic displacement, that using some of those figures that we showed last week to show how you could determine the plastic, we had a figure where you had your stress strain curve and you could determine your plastic displacement based on your load displacement curve. So you can determine your plastic displacement at any point. So this is ultimately an equation where when you're doing an experiment, you measure your distance between the cracks, you measure the current value of the load, your current value of your plastic displacement, you carry out this, you can determine the value of your J integral in the laboratory. And as I said, in a couple weeks, when we go into details on laboratory testing, we'll be going into these ideas in a bit more detail and fill in some of the gaps. But just one other note from this is that the unit thickness was assumed at the beginning of the derivation. In general, you have to take the plastic term divided by the plate thickness, and you take this term within the brackets here, and you normalize it by the net cross-sectional area of the panel, because the J integral has units of energy per unit area. But that's, this is just an idea where for this particular specimen geometry, the double-edged notch tension specimen, it's a way where just by in the laboratory where you're measuring crack lengths, distances between cracks, load, and your load displacement curve, how you can experimentally come up with the J integral, value of the J integral, okay? And yeah, so Just another example of another type of tests that can be done, that can be used to do this, is that Rice brought up in his article, is you have an edge crack plate in bending, as we show here, where you have your crack length A, your distance B from the crack to the end of the crack to the edge of the plate, and you're applying a moment. You're applying a moment, and you measure the angle from the horizontal, and you just call it omega over 2, and it's divided by 2 because you have on the right and on the left. And in this case, the folks who came up with this method decided to separate displacements get a little differently from what they did before. So the idea is that if you subjected it to, if you just had this specimen and you didn't have a crack at all and you started bending it, it would displace by an angle omega NC if no crack was present. And just because you have the crack, it displaces by an extra amount omega C. So the total angular displacement, you can just say that this omega, which is defined here, is equal to the non-cracked part of the angle that would just be without any cracking, and the change in angle that takes place due to cracking. Now, the one thing to keep in mind, if you have a really, really deep crack, this is really big compared to this. So the effect of this basically almost goes away. So you can say that the energy absorbed by the plate then is just equal to 0 to the current value of the rotation angle of the moment integrated over the angle. It's the same way where for a tension test, the strain energies, the area under a force displacement, under a stress strain curve. For this case, the energy for the case of the plate under bending is the area under the moment, the area under the moment angle curve. So now we talked about before, J is related to the derivative of, J is ultimately equal to the derivative of our strain energy with respect to crack area. So when we do this for this problem, only omega C, only the change in angle due to cracking contributes to the energy release rate, because since this omega NC, that's the change in angle that would just take place ordinarily if there wasn't any cracking. This omega NC isn't a function of crack size by definition. And by analogy with some of the derivations we did earlier, we can say that J is equal to the integral from 0 to current value of moment to the change in our cracked angle with respect to crack length as a function of moment, which is equal to negative 0 from m of the change in the crack angle with respect to the distance from the end of the crack to the edge of the plate, again, controlling the moment for a load control problem. So you're going to see when we go through over the next just little bit, this derivation is going to be pretty similar to what we did before. It's just instead of a tensile load and 2 cracks, we have a moment load and one crack. So if material properties are fixed, and we can, using similar ideas as before, and assuming once again that the only place you get plasticity is once again in this region here between the end of the crack and the end of the plate, because of your stress amplification. So we're doing that. So when you do all that, we can find that the change in angle in the crack zone is a function of the moment divided by the square of the square of the square of the of that b dimension. And like before, if the crack is deep, it's the same type of assumption we made before. This idea that we want the plasticity just being that region between the end of the crack and the end of the plate. So when we take this, we differentiate it with respect to B. So we'll take this and differentiate it with respect to B, and we'll substitute it into here. When we do all that, we end up with J is equal to 2 over B times the integral from 0 to omega C of M d omega C. Now, and you can see, so a lot of things are falling before, like I said, you'll see in just a few minutes, we're going to end up pretty close to where we were before, just formulated a little bit differently, and it'll be more in terms of energy. Now, note here is the decision to separate the angle into crack and no crack components was somewhat arbitrary. Could have divided the displacement into elastic and plastic components as we did before. And if the crack is relatively deep, this should be entirely elastic. This may contain both, this change in angle may have both elastic and plastic components. So we can rewrite, and we can say that J is equal to 2 over B times the integral from 0 to the elastic portion of the angle change, of the moment of the elastic portion, plus the integral from 0 to the plastic part of the moment d omega p. And when we take all this, similar to what we had before, we end up with J is equal to stress intensity factor squared divided by E prime, because it's our elastic component, plus 2 over B times the integral from the plastic part of the angle change of the moment of the plastic part of the angle change. And could have done so similar from what we had at all. And just to know, the prior analysis on the double-edged crack plate and tension, it could have been written in terms of displacement, if you didn't have any cracks, and added displacement because you have any cracks. But we were able to get simpler functions because in the previous problem, because we were able to assume that the ratio of the crack length to the distance between the cracks didn't matter. And, it was a reasonable assumption for our plastic displacements. So, but while elastic so this assumption was good for the problem we looked at, and trying to do this other idea so what we did was okay before, but if we tried to do this type of idea for the problem we looked at before, it wouldn't be quite as accurate. So you can combine the elastic and plastic displacements for the J integral and bending, but it's not so good to do it in tensile loading. So the idea that came from this Rice paper is, in general, the J integral for a variety of configurations can be determined to be some non-dimensionless constant times the strain energy due to cracking divided by the thickness and whatever dimension you choose for the distance between your crack and something else of interest, whether it's the edge of another crack or the distance between the crack and the end of the plate. And remember, B is equal to thickness, because for all the other problems we looked at, we assumed a unit thickness, but we have to obviously account for the idea that the plates we look at may just not have just unit thickness. So this equation expresses J as the energy absorbed divided by the net cross-sectional area. This is our net cross-sectional area times the dimensionless constant. And for our deeply cracked plate and pure bending, the problem we just looked at, this constant can be set equal to 2, which is why we got the equations we did. And we can take this equation we just had, and we can break it up into, in general, elastic and plastic components. So J is equal to K1 squared divided by E prime plus this constant times the strain energy due to the plastic part of the strain energy divided by the thickness and the B dimension. Okay, so it's just all this idea that it's just leading into ideas that if you separate out the elastic and plastic parts of things, which for some types of tests are easier than others, this is a way where from the laboratory, you can take load displacement. The whole idea of all of this is that you can take load displacement curves from tests on various types of specimens. And we're going to go into a bit more detail on this when we cover some more specific types of tests, but you can take low displacement curves, which is the common type of measurement you do in a fracture test, and from these you can compute the J integral to define the elastic plastic response. So even though some of these derivations were a little hairy, this is the big picture from this, that you can go from low displacement curves to determining the J integral. So the J integral is something that you can determine in a laboratory. So just as a sample, going back to that double-edged notch tension problem we had before, let's just say we define our load is equal, it's defined by a power law relation, that constant C times the plastic displacement to the n power. So given all that, we're going to take this general expression and we're going to use that and ultimately end up for a term for this non-dimensional constant. So the way we do that is we say that our plastic strain energy is equal to integral 0 to the displacement of C times the plastic displacement to the n power times the differential, and we do that integral, it's just equal to C delta P to the n plus 1 divided by n plus 1. And by applying this definition here, we can end up that it's equal to the load times the change in load over n plus 1. So we can take this and we can take this and manipulate our, so we can take this and we can go back to, yeah, so we can take this. We're going to go back to this we're going to go back to the equation that we developed when we looked at the double-edged notch tension problem originally. So originally we said that J was equal to K1 squared divided by E prime plus 1 over 2B times 2 times integral 0 delta P of P d delta P minus P delta P. And using this idea that we just came up with, that we just developed, and plugging in some of these derivations we just did for the definition of the plastic strain energy, we can say that J is equal to the elastic times the elastic part of the strain energy divided by big B times little b plus our plastic times this plastic strain energy divided by E times B, which K1 squared over E prime plus eta prime times the plastic strain energy divided by B times B. So if we take this and we basically take this, we set it equal to this, we apply this definition, we apply these definitions. Oh, we apply this definition here for how we apply P. So we take this definition for how we apply P, we plug it into this integral and do the integral and do the algebra, and then you compare to this and set it equal to that. So after some integration and algebra, you end up with this parameter is equal to P times delta P times 2 divided by n plus 1 minus 1 over P delta P divided by n plus 1. And by canceling lots of things, it's just 1 minus n. So you defined a relation between your load and your displacement. For the simple power law, that means that this non-dimensional constant, which you then can plug into this relationship, is very easy. So it's still, if you can do your load displacement in a power law relation, you can compute your strain energy as you go along using ideas we've talked about and plug this in. You can take your laboratory load displacement test and measure the value of your J integral. But as I said, it's just the math and some of this can get a little hairy, but just emphasize one more time, the big picture is you have a specimen, you define crack geometries, you take relevant dimensions, you take a load displacement test, you partition out the elastic and plastic parts from your load displacement test, and you manipulate them, and you can determine the value of the J integral from a standard mechanical test that's reasonable to do in the laboratory. Okay. So now we've talked about this J integral. Last week we talked about the crack tip opening displacement. So we talked about the relation between the stress intensity and the strain energy release rate before. Now we're going to talk about relationships between the J integral and the crack tip opening displacement. So for linear elastic conditions, where the conditions of linear elastic fracture mechanics was still applicable. We talked about the relationship between crack tip opening displacement and the strain energy release rate. And since for linear elastic conditions, the J integral equals the strain energy release rate, these equations also describe the relationship between the crack tip opening displacement and the value of J in the case where you just have small scale yielding and the assumptions of linear elastic fracture mechanics are still at least somewhat applicable. So what we had is we said that, we can say that J is equal to our dimensionless constant, which we talked about varies whether you're plane stress, plane strain, or something in between, times the yield stress multiplied by your crack tip opening displacement. So this is a simple version of the relationship, which is particularly applicable for small scale yielding. So if you have just a little bit of yielding. But now what we have is, say we have more yielding. So we want to see, okay, this relationship is fine and dandy for the case where we just have small scale yielding. What if you have more yielding? So the approach we're going to take is we're going to look at that strip yield zone idea that we talked about as a way of determining the crack tip opening displacement. And we're going to have a strip. We're going to look at the strip yield zone as we have here. And remember from before, as we talked before when we defined this, that we applied these artificial tractions along the crack tip that are serving to close the crack. That was the basic concept behind the strip yield zone. So we're going to take the strip yield zone where we have these artificial displacements that define that are serving that act as if they want to close the crack, and we're going to encase this, and we're going to use this as it's defined in this dashed line here. We're going to enclose the strip yield zone in a contour, and we're going to call that the contour where we do the integrals around to define the J integral. Now the first assumption we're going to make is we're going to assume that the damage zone, this area where we're adding our artificial stresses to close the crack, we're going to assume that it's long and slender so that the radius gyration is much, much smaller than our crack tip opening displacement. So because of that, in that area, it's going to make this dy term, the change in y, particularly near the end, the tip very, very small, because a long slender, this is kind of blown up and fat here, but if this is long and slender, the distance, these dy is very small. So since the only surface tractions within this area we're applying the stress are in the y direction, when we define our normals, we're going to say is that if the zone is basically like this, our normal to the crack face where we're doing our when we're doing our normal to the surface, it's basically just vertical because this is very long and narrow. So remember, we have that the traction is equal to the stress times the normal. And so if this is very small, we define our we take our stresses and the normal to this to any point where we take the stresses. If this is long and slender, this is almost horizontal. So we can say that the normal to this is just, so instead of what it looks like here, where the normal would be going off like this, we're assuming that it's long and slender enough that the normal's just vertical like that. So with all that, so we can go back and do our fundamental definition of the J integral, and we can just then say that it's our integral over our contour of our y stresses, because that's what's serving to close, and the derivative of our y displacement with respect to x times our increment along the contour. And again, we're assuming our stresses are also just vertical because it's a long and narrow damage zone. So then the other thing we're going to do is we're going to define an alternative coordinate system. We're going to assume that the origin of this alternative coordinate system's at the tip of the stress yield zone, and this x is equal to our rho minus x, So for a fixed crack tip opening displacement, and so with all that, so for fixed crack tip opening displacement, the stresses and the displacements only vary based on this x variable, provided rho small, and the J integral become, and we assume that that a crack tip opening displacement is 2 times is equal to this 2y dimension here. So with all that and all these assumptions, what we end up with is that our J integral is equal to 2 times the integral from 0 to rho of our stress as a function of x times dy, which is also a function of this big X with respect to x integrated over dx. And what we end up with is our integral from 0 to delta of stresses, y direction stresses, which are a function of delta integrated over d delta. And since in the stress strip yield model, we assume that this within the plastic zone that our stress was equal to the yield stress, we can just say that J is equal to the yield stress times the crack tip opening displacement. And this equation's real similar to our original definition of the crack tip opening displacement. We originally came up with it. We took a series expansion in the strip yield model. We took some equations and we did a series expansion, and we neglected the higher order terms, but we didn't need any assumptions for this new equation. So the strip yield model, which assumes plane stress conditions and a perfectly plastic material, predicts that M is equal to 1 under plane stress for both linear elastic and elastic plastic conditions. And an researcher called Sheep, and they go into details on this in the book. I thought that the math was just too hairy to go over here. Provided further evidence that a unique relationship between the J integral and the crack tip opening displacement applies well beyond the validity limits of linear elastic fracture mechanics. He evaluated the displacements at the crack tip implied by the HRR solution that we talked about last week, related the displacements at the crack tips to J and the flow properties, and he obtained an expression similar to the expression shown above. So the idea of all this is that even for cases where there's where there's a lot of plasticity, this relationship between the J integral and the crack tip opening displacement is valid, and they're just scaled by the yield stress. So we're about to change topics. This is a good break point. So we'll break here and we'll take back up about 6:15. Okay, we'll go ahead and get started. So now this is basically just closing the loop on some things. And so what we're going to do now is it's going to be several things where we talked about these concepts when we talked about linear elastic fracture mechanics, and we're just going to start talking about how they can be extended to the case where you have elastic plastic fracture mechanics. So for example, this idea of the crack growth resistance, the R curve. So many materials with high toughness, they don't fail catastrophically at a particular value of J or crack tip opening displacement. These materials instead they have a rising R curve where the J and the CTOD increase with the crack growth. And in metals, from a material science point of view, a rising R curve is normally associated with the growth and coalescence of microvoids. So this figure here schematically illustrates a typical J resistance curve for a ductile material. You can see this point here is where you start getting cracking and the crack grows, and your J resistance curve, it isn't just flat or straight, it has a rising R curve. So in the initial stages of deformation, the R curves relatively steep. There's due to crack blunting, there's a little bit of apparent crack growth, but as J increases, you start getting local failures at the crack tip and the crack advances farther. And because the R curve is rising, remember we talked about the point where we could say where the crack goes unstable. We talked about that a little bit for linear elastic fracture mechanics. The initial crack growth is usually stable, but an instability can be encountered later, and we'll talk about that in just a couple. We'll talk about that for just a couple minutes. So one measure of fracture toughness, J1C, kind of defined here in our schematic, is defined near the initiation of stable crack growth. Now, a point to note, like in many other things, the same way like a yield stress is hard to define exactly, the same way exact point where a crack starts to grow, it's hard to define if you're looking at an experiment because you're looking at a specimen and then all of a sudden picking up that specific point where it's starting to move from just a defined crack size to where you're getting a growth in the crack. It's not something that's easy to tell. So the definition of this J1C is somewhat arbitrary, the same way like the 0.2% offset yield stress when you're talking about a plasticity analysis is somewhat arbitrary. And the corresponding crack tip opening displacement near the initiation of the stable crack growth is determined as delta I by some of the testing standards. So so while the initiation toughness gives some information about the fracture behavior, the entire R curve gives a more complete description. So we can define as we measure the change in our value of J as our crack grows, we can determine the slope of this curve as defined here. So the slope of the R curve at a given amount of crack extension is how we determine the stability of the crack growth. A material with a steep R curve is less likely to experience unstable crack propagation. So if this is less flat and more like this, it's more likely to be stable. So for the J resistance curves, the slope's usually quantified by this term called the tearing modulus, and it's non-dimensional. So this tearing modulus is equal to the modulus divided by sigma naught, usually the yield stress squared, times current value of our slope of the JR versus crack length curve. And this subscript R indicates the value of J on the resistance curve. So this is a new parameter that will lead us to determine quantify the behavior of our R curve for elastic plastic analysis. Plus, it'll give us a way to define the stability, as we'll start talking about now. So the conditions that govern the stability of crack growth in elastic plastic materials are basically identical to the elastic case we talked about before. So instability occurs where we have these instability occurs where the driving force is tangent to the R curve. So we have our R curve and we have our driving force curves. We talked about all this before the elastic case, and just like before, when they intersect, this is where you start getting instability. And also, like we talked about before, load control is usually less stable than displacement control, because it's just at this point here in the displacement control curves where we get instability. So all this, it's just the curves are a little more nonlinear, but the ideas are the same as we talked about before when we talked about linear elastic fracture mechanics. And the conditions in most structures are somewhere between the extremes of load control and displacement control. Makes sense. Load control and displacement control are nice laboratory scale types of tests. Real structures don't behave like they do in the laboratory. So the intermediate case can be represented by a spring in series with the structure where the remote displacement is fixed. And I didn't copy over the figure, but it's the idea we talked about before, where we had the structure and we had our spring and we also had the load control. So since the R curve slope, we represent that by dimensionless tearing modulus, we can express our driving force, the P here, in terms of the applied tearing modulus, and we can say that our apparent tearing modulus is equal to our modulus divided by our yield stress squared times our slope of our J crack length curve for a specified displacement. And this delta T here is a local remote displacement that we can define as follows. So our local displacement is equal to our displacement plus the system compliance times the load. So this defines our total remote displacement. So we have so we have the displacement, our far field displacement, add in the extra terms in the displacement due to the fact that we have a crack there. We use that as our displacement. We evaluate our dJ/dA curve at that point, and that gives us our apparent tearing modulus, which defines our resistance curve and our stability. And the slope of the driving force curve for a fixed delta T is just like we did for the linear elastic case, only instead of G, we use J. So we can say, and so this is same equation that we had before. So dj dA at delta t is equal to the derivative of j with respect to A for A holding the load constant minus the derivative of j with respect. And we're going to do an example in a minute where we compute some of these derivatives. We'll give a specified relation. We'll compute some of these derivatives. So it's minus dj dP for specified A multiplied by d delta dA for specified P, all of that multiplied by our system compliance plus the derivative of our displacement with respect to load for specified crack length, and we invert this. Now for load control, this CM term here, so for load control, CM goes to the system compliance goes to infinity. So if this is infinity, that takes this thing to infinity. You invert infinity, it's undefined, so that makes all of this go away. So for the case of load control, it's very easy in just that the derivative of j with respect to A for the case for this total remote displacement is equal to the derivative of j with respect to the crack length at the value of our load. And conversely, for displacement control, the CM goes to 0, and as makes sense, this total remote displacement is just equal to our applied displacement, which makes sense because if we're applying the displacement, then that's our baseline for which everything is based on. So during stable crack growth, we can say that for stable crack growth, our value of J has to be equal to JR, and that our applied tearing modulus is less than or equal to our apparent tearing modulus is less than or equal to the TR term that we described before. So just a simple example of how to apply this. Oops. And also unstable crack propagation takes place where our apparent tearing modulus is greater than the TR term that we described. So a simple example of how to apply this process is shown here. So we have a double cantilever beam specimen with the spring in series, and we assume overall it's linear elastic conditions. So from an example we did before where we looked at this, we found that J is equal to strain energy release rate was equal to P squared times A squared divided by the thickness times the modulus times the moment of inertia. And our displacement was equal to 2p A cubed divided by 3EI. So given all that, we go to this equation here that had all of these partial derivatives. And we now have specified relations for our J and our displacement. So with that, we can say that our derivative of J with respect to A is equal to 2p squared A divided by BEI, and the derivative of J with respect to P, holding A constant, is equal to 2P A squared over BEI, and the derivative of delta with respect to A is equal to 2P A squared over EI, and the derivative of delta with respect to P, holding A constant, is equal to 2A cubed over 2A cubed over 3EI. So we take all of this and we plug that into our equations. We know that our parent tearing modulus is equal to E over sigma naught squared times dj dA at the value of delta t. And we know that dj dA delta t is equal to dj dA at P minus dj dP at A times d delta dA at P, all of that multiplied by Cm plus the derivative of delta with respect to P, inverse that. So this is the equation we defined before. We take all of these derivatives, we plug it in here, and we do some algebra, and we end up with our parent tearing modulus equal to 2 times P squared times A divided by sigma naught squared BI 1 minus 2 A cubed divided by EI, all that multiplied by Cm plus 2 A cubed over 3 EI, negative to invert that. So we have a defined geometry, and from the defined geometry, we defined our J integral and our displacement, and from all that, we were able to compute our tearing modulus. Okay. So just a couple other points on this. As discussed earlier, the point of instability in a material with a rising R curve depends on the size and geometry of the crack structure. Critical value of J at instability is not a material property if J increases with crack growth. And it's usually assumed that the R curve, including the J1C value, is a material property independent of configuration. So this is the reasonable assumption, but just keep in mind that if J changes if the variability of J changes with crack growth, that the assumption may not be so valid. So it's just something to be careful about, that always make sure that your actual condition fits the idealized conditions under which certain situations were set. Okay. So now, a couple other points, computing J for a growing crack. So the geometry dependence of a J resistance curve is influenced by the way in which J is calculated. All these equations that we derived earlier were based on the energy release rate type of definition of J, and thus are valid only for a stationary crack. Now, there are ways to compute J for a growing crack, including the deformation J and the far field J. So we're going to describe it just qualitatively below. And the former method, the deformation J, is what's usually used to obtain experimental J resistance curves. So this figure below illustrates the load displacement behavior in a specimen with a growing crack. And remember that the J integral was based on the nonlinear ideas of nonlinear elasticity, the deformation plasticity. So we kind of assume that things are following this path. But for a growing crack, it's actually following this crack here above the hash line. So if you look here, we're assuming that the crack has grown to a length A1 from the initial length A0. So if the material was elastic, so this is our load displacement curve, the solid line. So this area here, this hashed area, cross-hatched area, this is the area that would be released if the material was elastic. Now, when an elastic plastic material, only the elastic part of the energy is released. Oh, come on. But what we have is the remainder of the energy is the energy is not released, but instead what happens is you have this plastic wake behind your crack, and this is what absorbs the energy for an elastic plastic problem. So this is just something to be cautioned about. So in the elastic material, all the quantities, including the strain energy, are independent of the loading history. But in an elastic plastic material, if you have crack growth, because you have extensive plastic flow, and plastic flow by definition is a history dependent phenomena. So the energy absorbed during crack growth in an elastic plastic material exhibits the history dependence. So this dashed curve in the figure, so this dashed curve here, this dash curve here, represents the low displacement behavior in the crack size that's fixed at A1, and the area under this curve is the strain energy in a nonlinear elastic material. So this is the elastic energy. This is for the nonlinear elastic case, for the case where A equals A1. This is our strain energy for our nonlinear elastic material. And defined here, specified here, this U sub D. So even though the actual loading goes like this, by our assumptions that we follow nonlinear elasticity, we only consider this light gray area as the strain energy that we're going to consider. So this energy depends only on the current load and crack length. So we're going to define this U sub D, this strain energy is equal, and it's only a function of the current load and the current crack length, which is equal to the integral from 0 to our current displacement of our load displacement curve, assuming that the crack length is at the point where the crack length is equal to our specified A1. And the J integral for a nonlinear elastic body with a growing crack, it's defined by this equation. So the J for this case is equal to -1 over B times the derivative of this U sub D strain energy that we talked about with respect to the crack length for over displacement, which is equal to this non-dimensional term beta times the strain energy U D divided by the thickness and our B dimension. So our J sub D is equal to the elastic part, K1 squared over E prime plus eta P U sub D for the specific value of load divided by B times B times, I think this is a typo, B times B. So the So it's similar to before, only this is different because we have our growing crack, where before we assumed that our crack was stationary. So when the J integral for an elastic plastic material is defined by the above equations, the history dependence is removed and the strain energy release rate interpretation of J is restored, because we're accounting for the special case. We're saying, okay, what if it's behaving as if it's a nonlinear elastic material, and we know that our crack is here, so we're assuming if just everything just progressed along the way as if it was a nonlinear elastic material, unlike the real loading case where our crack actually grew from A0 to A1. Yeah, man. So the deformation J is usually computed using this equation here, because no correction is required on the elastic term as long as the stress intensity factors determined from the current load and crack length. And the calculation of this UD is normally performed incrementally, because the deformation theory load displacement curve depends on the crack size. Because if because we had this here, and if the crack changed again, and we're here, we'd have a new curve, equivalent load displacement curve. So we'd have a new area under that equivalent load displacement curve, and thus a new strain energy. Yeah. Okay. And you can also determine a far field J from the contour integral definition, which may differ from this JD. So Rice et al. Showed for a deeply cracked bend specimen, the far field contour integral in a rigid, perfectly plastic material. It can be said that. So he defined an alternate definition of J, which is equal to 0.73 times the sigma naught times the integral of 0 to omega, defined as we talked about before, d omega. So this is that crack bend specimen, and just using that, you can use alternate definitions even for a growing crack to compute an alternate definition of J. And then by using the idea of deformation theory, you would then get that this JD is equal to 0.73 sigma 0 times B times our crack angle. Now, the two expressions are identical when the crack is stationary. Now, the nice thing is that people have done finite element calculations, and for a 3-point bend specimen with a strain hardening material, if your crack growth is only moderate, this expression here is equal to this expression here, and similar to this expression here. So for moderate amount of crack growth, these alternate methods all pretty much give the same results, which is good. Now, so the J integral from the contour integration is path dependent when the crack is growing in an elastic plastic material, and it tends to 0 as the contour shrinks to the crack tip. And there's no guarantee that either of these methods will uniquely characterize the crack tip conditions for a growing crack. So if you have a situation where they don't uniquely characterize the crack tip conditions, then this JR curve becomes geometry dependent, which makes it not viable for use as a material property. But as I said, for as long as the cases where your crack growth is moderate, the assumptions are reasonable and everything works out okay. But it's just this, once again, a case where we assume idealized conditions, and when you do things, you just always have to be a bit cognizant that if you're outside of the norms for which your idealized methods were developed, that things may not fit within the parameters as given by the nonlinear, by the idealized derivations. Okay. So we talked about K-controlled fracture before. Now we're going to talk J-controlled fracture. And this term J-controlled fracture corresponds to situations where all the assumptions do work and J completely characterizes the crack tip conditions. So in this case, there's a unique relationship between J and the crack tip opening displacement. J-controlled fracture implies CTOD controlled fracture, and et cetera, and vice versa. But just as there are limits to linear elastic fracture mechanics analyses based on J and CTOD become suspect where you either have lots and lots of plasticity or lots and lots in crack growth, in which case the relationships depend on the size and geometry of the structure or test specimen. And the problem you have in anything like that is that you have all of your you basically have your data from controlled coupon tests, so you just have to realize that if the conditions in your real structure don't fit within the bounds that your coupon test was done, that all this data you have from your coupon test may not be valid. So here are some of the required conditions for J-controlled fracture, and we'll talk both about fracture initiation from a stationary crack and stable crack growth. So we have this figure here, and it schematically illustrates the effects of plasticity on the crack tip stresses. So we're applying the vertical stresses sigma yy and plot it against the normalized distance from the crack tip. And this characteristic length scale L corresponds to the size of the structure. So it could represent, for example, an uncracked ligament length. So part A, so this part A of the figure here is the small scale yielding case where you just have a little bit of plasticity. So this very, very light gray is just your far field. This little darker gray is the K-dominated zone, the zone of linear elastic fracture mechanics. This zone is where J integral is valid, and this zone here, where in this case is really small, where you have lots of plasticity, where all the things we talked about may not work. So at a short distance from the crack tip relative to L, it's where the linear elastic fracture mechanics is valid and the stress is proportional to 1 over the square root of the radius, and that's how we're defining our K-dominated region. Then we're assuming monotonic quasi-static loading. A J-dominated region occurs in our plastic zone where the elastic singularity no longer applies. And well inside of the plastic zone, this HRR relation that we talked about last week is valid, where we have our stresses are just at the plastic stress, yield stress, and everything is valid. And the stress varies in this zone as a function of r to the -1 over n plus r over negative to the -1 over n plus 1. And then the finite strain region occurs within a distance 2 delta from the crack tip, where large deformation invalidates the HRR theory. So in small scale yielding, K uniquely characterizes the crack tip conditions, even though the 1 over square root of R singularity doesn't exist all the way to the crack tip. And J uniquely characterizes the crack tip conditions, even though the deformation plasticity and small strain assumptions are invalid in the final finite strain region, but this finite strain region is relatively small. Now, the next step in this process, now if we go to this part B, now this is a zone where this is elastic plastic conditions. There's no longer a zone that's subject to linear elastic fracture mechanics. You see in part A, we have this region where our slope's equal to -1/2, and everything grows nicely, and it's just about here where it starts to break. Now, we never have anything that fits within the parameters of the linear elastic fracture mechanics, but the HRR conditions, the J conditions, are still approximately valid, excuse me. So as the plastic zone increases in size, the K-dominated zone disappears, but the J-dominated zone persists. And even though K doesn't have any meaning in this case, going back, yeah, so K doesn't have any meaning in this case, but the J integral is still an appropriate fracture criterion. And since J implies CTOD, crack tip opening displacement is also still valid. Now, the final case, if you have lots and lots of plasticity, very large plastic strains, in this case, neither K or J are valid. So the size of the finite strain zone is really, really large. There's no longer a region uniquely characterized by J, and single parameter fracture mechanics is invalid in this region, and any of your critical values exhibit a size and geometry dependence. So what this means, why you have to be careful, is that in certain specimen and structural configurations and certain loading conditions, the K and J zones are very, very small, and a single parameter description is not possible except at very loads. Now, it's important to emphasize that J dominance at the crack tip doesn't necessarily require the existence of an HRR singularity. All it requires is that the defining relations are valid in the process zones near the crack tip where the microscopic events that lead to fracture occur. And the HRR singularity is just one. So it's in this zone because in reality, because always remember, it's actual stuff going on in the microstructure of your material that leads to fracture. So if the stuff going on in the microstructure your material is still happening in this zone where the J characterization is valid, it's it's okay. So the HR singularity is just one possible solution to more general requirement that J uniquely defines the crack tip stresses and strains. And part of it's because the flow properties of most materials don't conform to the idealization of a Ramberg-Osgood power law on which the HRR analysis is based. And even in a Ramberg-Osgood material, the HRR singularity is valid just over a limited range, and large strain effects invalidate it close to the crack tip, and the computed stress lies below the HRR solution at greater distances because you have lots of plasticity, which leads to lower stresses. So this effect, so if we go back to what was employed, the methods that were employed by Hutchinson, who he took the stress, defined it as an infinite series, and showed that the leading term was proportional to the radius to the -1 over n plus 1. And the singular term, as R gets to closer to 0, the singular term dominates, and higher order terms are only significant for moderate values of R. So when the computed stress field deviates from HRR, it still scales with J divided by sigma naught times R. So J dominance doesn't necessarily imply agreement with the HRR fields. And simple relationships also become invalid as your specimen boundaries interact with the crack tip. We generally, when we derive all this stuff, we assume that our cracks are just sitting in the middle of an infinite zone. So when we start getting to the point where edge effects start coming into play, then it becomes a different ball game, and the linear elastic fracture mechanics solution also breaks down when the plastic zone size is a significant fraction of the in-plane dimensions. And as you start growing your plastic zone, the crack tip conditions, and we talked about this some before, start evolving from plane strain to plane stress as the crack tip plastic zone size grows to a significant fraction of the thickness, and when the large strain region reaches a finite size relative to the in-plane dimensions, the J integral also breaks down. So just all these are just cautions to consider. And other cautions to consider are, according to the arguments that we just talked about, J conditions at the tip of a stationary crack provided J conditions exist at the tip of a stationary crack provided the large strain region is small compared to the in-plane dimensions of the crack body. Now, once we start having crack growth, it introduces another dimension, the change in length from its original length to the current length. So once your crack starts growing to a particular point, J, it may have been just fine before, but it may not characterize the crack tip conditions when the crack growth is significant compared to the in-plane dimensions. Now, prior crack growth shouldn't have any adverse effects in a purely elastic material because our local crack tip fields only depend on current conditions. One of the things in elastic analysis, you have a strain, you multiply by modulus, you have a stress. It doesn't matter how you get there. But because in the case of plasticity, your plastic strains are dependent on how you get there, so your strains and stresses in an elastic plastic material are influenced by the prior loading history. So when you have a combination of significant plasticity and crack growth, the J integral theory may break down, and can look at it both from an analytical, we're not going to go into it here, but can go in from an analytical point of view and from an experimental point of view. So under J controlled conditions, we have, you have a growing crack, and under J controlled conditions, some of the material behind the growing crack tip is actually unloaded elastically. So based on earlier discussions, we compared the unloading behavior of nonlinear elastic and elastic plastic materials. The unloading region here, because we talked about, if you have a real stress strain curve, nonlinear elasticity assumes that you go back along the way you came. But if you have elastic unloading, that means you behave like plastic materials normally do, and you have permanent plastic strains in there. So this material in this elastic unloading regime, which acts like this, violates the assumptions of deformation plasticity, which all of our derivations were based on. And some of this material directly in front of the crack tip also violates our assumptions because we have non-proportional loading, which means that the stress components change at various rates and some components actually decrease. So in order for this crack growth to be J controlled, the elastic unloading and the non-proportional plastic loading regions have to be embedded within a zone of J dominance. When the crack starts growing outside of this zone of J dominance, the measured R curve is no longer uniquely characterized by J. So as long as all of this complicated stuff occurs within our J dominated zone, we're okay. But when the crack grows to the point where it gets out of this J dominated zone, we start having problems. And in small scale yielding, there's always a zone of J dominance because the crack dip conditions are actually defined by the elastic stress intensity, which only depends on the current values of the load and crack size. And the crack never grows out of the J dominated zone as long as all the specimen boundaries are remote from the crack tip and the plastic zone. So this slide here just has in words what I just talked about. So this figure here illustrates how our illustrates the three distinct stages of the crack growth behavior in small scale yielding. So under the initial stage, the crack is essentially stationary, and the steep slope of the R curve is caused by blunting. And we can define our crack tip fields for stage one. We can say that it's our stress divided by our sigma naught term is equal to some function valid for stage 1 of E prime times J divided by sigma naught squared R and our angle theta. Now, when we go to stage 2, we start growing this stage here, stage 2. This is where we start growing our crack. So the crack stresses and strains, they're influenced a little bit by the original crack tip behavior by the early stages of crack growth, but we can say that at the start of stable tearing, we get that our stress divided by our yield stress is equal to a function valid for region 2 of, it's a function of E prime J over sigma naught squared R again and theta again, but it's also now a function of our change in crack length divided by our crack tip opening displacement. And then finally, we're going to look at zone 3, where we have just steady state crack growth. So when the crack grows well beyond the initial blunted tip, reach a steady state condition, and the local stresses and strains are independent of the amount of crack growth, because we're saying that no matter how, went a little too far, no matter how the crack continues to grow, our value of J just remains constant. So in this zone 3, we have sigma ij over sigma 0 is equal to some function of E prime J over sigma naught squared R and theta. So even though this equation and this equation would predict identical conditions in the elastic singularity zone, the material in the because of the history dependence, the material in the plastic zone of a tip of a growing crack is likely to experience different loading history from material in the plastic zone of a blunting stationary crack. So these two functions are not equal as the radius goes to 0. And during steady state crack growth, a plastic zone of constant size, this idea here that we get this plastic wake here, sweeps through the material, leaving a plastic wake. The R curve's flat, J doesn't increase, and as long as the material properties don't increase with position. So if this equation applies for the zone 3 response, J uniquely describes the crack tip conditions independent of crack extension. And if the material fails at some critical combination of stresses and strains, then the local failure at the crack tip must occur at a critical J value, just as in the stationary crack case. And because our curve is flat here, because our J curve is flat here, this critical J value remains constant with crack growth. And if we had a rising or following R curve, it would mean that it would be due to the fact that the local material properties are varying with position. So the second stage here, just a little more detail on this, it corresponds to the transition between the blunting of the stationary crack and the crack growth under steady state conditions. So as you see here, a rising R curve is possible. So in this case, in this zone here, we can have that our R curve J is some function of our change in crack length, so under small scale yielding conditions. So this JR curve can be considered a material property. During the blunting stage, the plastic zone expands during loading, but the crack doesn't extend by ductile tearing. Under the steady state conditions, ductile tearing occurs. We get crack growth, but we have a constant plastic zone size. And during the transition from blunting to steady state crack growth, ductile tearing and plastic zone expansion occurs simultaneously, resulting in a rising R curve. Now in laboratory tests, the steady state limit is usually not observed because in typical test specimens, the ligament is fully plastic during crack growth. Therefore, you don't have small scale yielding, which violates the assumptions. And the crack also approaches the finite boundary while still in stage 2 growth. So you would need to have really big specimens to observe steady state crack growth in tough materials. So that's what we have. So this is our introduction to plastic fracture mechanics. Okay. Okay, so as I said, next week what we're going to start talking about is actually how to go into more detail on all these things for linear elastic and elastic fracture, plastic fracture mechanics. We're going to talk about how we measure some of these things in the laboratory. So if there's nothing else, have a good week, and I will see you next week. And don't forget your homework's due next week.